Subscribe now and click on the bell icon to never miss learning from Vedantu.
This is the kind of graph that we are getting. Okay, rectangular hyperbola. Actually, it is not like that. It is slightly like this. It will be right. So in this case, see here, this is going almost parallel to this. This is going almost parallel to this. That is the reason it has given the name as rectangular hyperbola. So if volume is 0, that means if it goes like this, that means the pressure should be infinity. That means here it is. It should, the volume is 0 means it should touch this one, isn't it? This way, if it goes. The pressure has to be infinity. Very high value of pressure. And the other way around. If volume is infinity, it goes like this, the pressure will be almost 0. So that is. Now the question still remains as to why are we getting a graph like this, pressure versus volume, this kind of graph, a hyperbolic graph, why are we getting? Why are we not getting this kind of a linear graph? That question still remains, isn't it? This is because when pressure increases, volume decreases, we said, isn't it? When they come closer, molecules, they come closer, there are attractive forces and also repulsive forces. So therefore, the increase in pressure does not lead to the same decrease in volume. It will not be constant. It depends upon the kind of intermolecular forces of attraction and repulsion that are in play there. Okay, that is the reason you don't get this kind of a graph. Okay?
Yes.
Let us move ahead to the next one. There is a simple problem based on this. P1 V1 is equal to P2 V2. So 1 liter sample of a gas at 760 torr. Torr is mm, okay, millimeter. Torsil, the scientist was there. So in his honor, they have kept this as torr. It is compressed to 0.8 liter at constant temperature. Calculate the final pressure of the gas. What do you think? Pressure will be higher or lower?
So the volume is decreasing.
Volume is decreasing, yes.
So pressure will increase.
Pressure increases, yes. You should get the pressure more than this. That is correct. So if you do it, P1 V1, so 1 into 760 is equal to 0.8 into P2. 760 divided by 0.8. $950, correct?
Yes, ma'am.
950 torr, or is equal to 95 centimeter, whichever way you can calculate it. This is a simple problem. Okay, yeah. This is correct. Let us move on to the next one. Okay, so in this case, this is a relationship between volume and temperature. So naturally, pressure and number of moles must remain constant. Okay, so this is our day-to-day experience. You must have seen water boiling, isn't it? Boiling water and there is a lid here. So then the lid is pushed. Correct? The lid comes out. You must have observed this, isn't it? So because it is open to atmospheric pressure, pressure remains constant there. So as you increase the temperature, volume also increases. So that is the direct relationship between volume and temperature. Now similarly, as in the previous case, if the state changes from initial to final state, then T1 is the initial volume, V2 T2 final, and then you will get this relation, simple relation. That is V1 by T1 is equal to V2 divided by T2. Okay, this is regarding Charles' law.
The temperature's in Kelvin, ma'am, here.
Always. We keep temperature in Kelvin only. We use degree centigrade only to measure the temperature. And later on we are going to convert this into Kelvin only. None of the calculations are done using degree centigrade. Remember that. Okay? You have to convert it into Kelvin.
Ma'am, what will happen if you use...
You will get a different value. Nowhere we use this small t. We always use this capital T. Capital T means Kelvin scale.
Okay.
Okay. Only in certain cases when it gets cancelled, you have a ratio. If both of them are in degree centigrade, you can use it. That's it.
Okay.
Because in any case the unit is going to get cancelled, not otherwise. Okay, here also we have got a similar kind of graph here. So, isobars it is. The plots that are plotted at constant pressure, they are called as isobar. Bar is something related to pressure. Okay. So, isobars, just like isotherms, constant pressure graphs. So, in this case, this graph is done at 3 different pressures, P1, P2, P3. Which one is the correct one? P3 less than P2 less than P1. How do we get that? So you can draw a line like this, pressure, volume, or like this, horizontal or vertical line, whichever way you want. Okay. So this is the highest temperature. So all this pressure also should be highest. Pressure and temperature also have got a direct relationship. Okay. See, that is what you see here. Okay. This is slope of a straight line, this slope. That slope you will get this K, constant K. Y is equal to mx. C is not there because it is starting from the origin. Okay, so this K is nothing but the slope of even in the previous case. That is what you asked, I think so, correct? So the slope is nothing but the value of K here. See here? This M.
Yes, ma'am.
Even in the previous case, okay? So, yes.
So volume is inversely proportional to, indirectly proportional to 1 by temperature.
Y directly proportional to temperature. V is directly proportional to T. Direct relation. That means as temperature increases, volume also increases. But pressure and volume, they have an inverse relation. As pressure increases, volume decreases. Okay, this is a direct relation.
Yes, ma'am. But sometimes, like when we do the salt analysis and all that, while we heat it, that time sometimes the volume decreases, right?
And that is due to evaporation. You will have lost some matter into the atmosphere. There, the amount of the substance is not constant. All these laws are applicable only if you keep N constant. Okay, because you will be doing all those experiments in open vessels, isn't it? Open test tubes, correct?
Yes,
Some of the matter, it would have escaped in the form of vapor.
yes, ma'am. When you do the dry heating, right, that time they ask us to check.
Correct. In that case, this law is not applicable because you have lost, if we have not kept the amount of the substance constant. Okay. In all these cases, amount should be kept constant. See the, statement of this law. Where is it? So they have increased this number. Yes, one. It is telling me that has been restored. Okay, fine. Now it is okay.
Yes, ma'am.
Yeah. If some connection has been lost, it says. I don't know, it is some problem there. It's okay. Yeah, this is fine. So now, I will show you that. Okay, right. This one. For a given mass of a gas, at a given pressure, the volume of the gas is directly proportional to absolute temperature. Given mass means the amount of the gas should remain the constant. Okay, then only this law is applicable. Okay. So this graph is also very, very important. Right? Okay. This is another extension of Charles' law. What happens is, when we draw the graph like that, so see here, this volume and this is temperature. Okay, in the previous one, I think we had taken, it is the same, volume and temperature, it is the same. So in this case, as temperature decreases, volume is also decreasing, am I right? And it is going to reach this volume here, this temperature, zero temperature here. And beyond that also we can cool, -5, -10, up till here. When it comes to this graph wherein volume is zero, it becomes -273 degrees centigrade. So this is the lowest temperature. We have not been able to attain this temperature. So this is the temperature at which theoretically the volume of the gas should be zero. Correct? This is called an absolute zero of temperature. So because the volume cannot be zero for the gas, it must occupy some volume, isn't it? So this is, we can say that at this temperature, gas doesn't exist in that state. So that is absolute zero. Okay?
So it's only theoretically this.
It is only theoretical, yes. Because see, we are extrapolating it to that temperature. Okay?
Yes, ma'am.
So it is the temperature at which the volume of the gas becomes zero, absolute zero of temperature. So this is the basis for our Kelvin scale. See here. Kelvin scale, it is this one. This is -273 degrees centigrade. It is 0 Kelvin. 0 of Kelvin scale. So because this is the lowest temperature and we start from 0, there is no negative Kelvin values. We don't have. That is the advantage of that. Because 0 Kelvin itself is the lowest temperature, -273 degrees centigrade. Okay, so that is the reason if you want to get any temperature in Kelvin scale, if you want to convert degrees centigrade, you just add 273 to that. That's it.
Yes, ma'am.
Okay. So Kelvin scale temperature is equal to any temperature in degrees centigrade plus 273 point, to be more specific, 16. For all practical purposes, we take it as 273. Okay. Supposing you want to convert 25 degrees centigrade, just add 273 to this. That's it. So temperature in Kelvin will be equal to 273 plus 25, which will be 298 Kelvin. That's it. Okay. In fact, this is the advantage of our Kelvin scale. There are no negative values here, only positive. It starts from 0. Okay.
Yes, ma'am.
Let us take up the simple problem. A sample of gas at 1.20 atmosphere and 27 degrees centigrade is heated at constant pressure to 57 degrees centigrade. Its final volume is 4.75 liter. What was its original volume? So you can use T1 by V1 is equal to T2 by V2. That expression we can use. Somewhere here it was. This one.
V1 by T1 equal to?
Yeah. Either way. V1 by T1 is equal to V2 divided by T2. Even if you write it as T1 by V1 is equal to T2 by V2, you will not get a different answer.
Yes, ma'am. Just reciprocal.
Yeah, just reciprocal. Both the sides we will have to do. Right. So V1 by T1 is equal to V2 divided by T2. Just see how much is the value that you are getting. You have to convert both temperatures into Okay, so you can cross multiply 1 here. V1 by V2 is equal to T1 by T2. What is the value that you're getting? See, it has been done here. 4.32 liter. You got the same answer?
No, ma'am, I forgot to convert. So
if you don't convert, you will get a different answer.
Yes, ma'am.
Okay, yeah. Okay, fine. Let us move on to the next law, which is a relationship between Gay-Lussac's law. Gay-Lussac's law is just like Charles' law. Charles' law is the relationship between V and T, and Gay-Lussac's law will be the relationship between P and T. Okay, that is the only difference. Otherwise, everything else is the same. For a given mass of a gas at constant volume, there it was pressure constant. Here it is volume constant. The pressure of the gas is directly proportional to its absolute temperature. So that means volume is directly proportional to temperature. Pressure is also directly proportional to temperature. Temperature increases, pressure also increases. Okay, so that is this equation. So slope will be K in this case. So we are going to get a graph like this, linear graph. So similarly, we should be able to find out what is V1, V2, V3, etc. You can do the same thing here also. Draw a horizontal line or a vertical line. Whichever way you do, you can find out this. This is highest temperature. So V1 should be the highest volume. Okay, V1 greater than V2 greater than V3.
Yes, ma'am.
As volume increases, the curve becomes so steep, so K value decreases. That is another, generalization that you can make. The value of K here decreases as the value of V increases. Okay, this is what is becomes slant, isn't it? That is the reason. Right.
Yes.
Let us move on to next year. There could be one question. Avogadro's law. This we had done in basic concepts also. That is Avogadro's law. V is directly proportional to number of moles provided pressure and temperature remains constant. That is how we defined molar volume, standard volume of a gas, isn't it? 1 mole of any gas would occupy a volume of 22.4 liters at STP, correct? At STP means temperature and pressure have remained constant. 1 atmospheric pressure and temperature is 273 Kelvin. These two when you keep constant, the other two must be proportional to each other. That is what this law is. That's it. At constant pressure and temperature, the volume of a gas is directly proportional to the number of moles of the gas.
Yes.
Alternatively, we can define this. Alternatively, at constant temperature and pressure, equal volumes of all gases will contain equal number of moles. Since mole is directly related to number of molecules, we can also say that they will have equal number of molecules. Okay, so that is how we got 1 mole of any gas at 1 atmospheric pressure, 273 Kelvin, occupies the volume of this. We call this as standard molar volume, 22.4 liters. Okay, so this is at 1 atmospheric pressure, but if you consider 1 bar pressure, nowadays even this is considered 1 bar pressure, this bar is slightly lesser pressure than 1 atmospheric pressure, so we will get little larger volume, that is 22.7 liters. Okay, don't get confused if this value is given Hardly any difference is there. Only at one bar it is, not at one pressure. So in that, generally we call it as the NTP. Normal temperature and pressure. Okay?
Yes, ma'am. Even for number of moles, we can substitute mass by molar mass and get.
Yeah. Number of moles?
We can substitute mass by molar mass and find.
You can always. Number of moles is equal to N is equal to mass divided by molar mass. This you can use wherever you want.
No, we can substitute in this equation. If
we can substitute.
To find molar mass.
If required. Questions are there like that. That we can substitute. Okay, yes. So this is a summary of all the laws what we studied here. Okay, which are the two constants, it gives an idea here. Okay, now what if you combine all the gas laws? You will get an equation like this. PV is equal to nRT, which is a combined gas equation. Combining all the gas laws, we get this equation. PV is equal to nRT. This is known as ideal gas equation. Because all those gases which obey this law, they are called as ideal gases. Okay? This is ideal gas equation. PV is equal to 1 hour. Lot of application it has. Okay? So this, using this equation, we can find out the value of gas constant, universal gas constant R. How do you do that? Do that PV divided by N into T. Okay? Pressure, 1 atmospheric pressure, let us suppose that we will do it at STP. So 1 atmospheric pressure, volume occupied by 1 mole of gas is 22.4 liters. This is 1 mole into temperature 273 Kelvin. When you do this, you will get that right. You can check it. 22.4 divided by 273. 0.0821. All these you can have to write. Atmosphere, liter, per mole, per Kelvin. Okay? This is the value. This is what you have got here.
So this value is always constant, ma'am?
Yeah, if you want this value, then you have to substitute in Pascal. Atmosphere, Pascal you have to do. Okay, you can try this. Substitute the pressure in Pascal, volume in meter cube, temperature of course in Kelvin, number of moles of course remains the same. When you do that, you will get this value. Joules per mole per Kelvin. Okay. Next is, we can also do it in calories. This can be converted into calories. So 4.2 joules is equal to 1 calorie. Right? Then 8.314 joules is equal to how much? 8.314 joules divided by 4. You will get it in calories. Into calorie. This is joules. Joules get cancelled. So it is slightly 1.98, you will get 8.31, 4.4, yes, slightly less than that. 8.314 divided by 4.2. 1.97, close to 2. Correct? This value. Sometimes we use this also.
So depending on the units, the value of R changes.
Changes, yes. And you should see, generally they will give you this value. In problems, they will provide this unit, this value of R. Don't have to, remember, and you don't have to try. You know how to derive it, even if it is not there. You know how to do that, isn't it?
Yes, ma'am.
So now, one important relation here I would like to tell you is next chapter, thermodynamics, we are going to use it. Okay, so there we are going to find out the work done in terms of liter atmosphere. There is one way of doing that. but work done is not kept in this unit. We have to convert this into joules. For that you require this. Okay, how do you do that? See here. 0.0821 liter atmosphere per Kelvin per mole is equal to 8.314 joule per mole per Kelvin, correct?
Ma'am, the screen is
It's not. Oh,
is like stuck.
it is stuck. Oh. Here it is showing it is not. Okay, let me do it and let me open it. Now it is okay?
Yes, ma'am. Yes, ma'am.
It was stuck there. Fine. Now it is okay. Yeah. See all these problems. Why? I don't know. Maybe because of this rains or something like that. Earlier this problem was not there. Okay. So like this. So these two you have to equate. And then this Kelvin per mole they get cancelled. Correct? You will get 0.0821 liter atmosphere is equal to 8.314 joules. And 1 liter atmosphere is equal to 8.314 divided by 0.0821 joules. This we will be using there, so you will have to remember this. Not the value. I don't want the value. How to get it? Okay. 8.314 divided by 0.0821. You will get 101.2. 1.2 joules. Okay. We will be using this. 1 liter atmosphere is equal to 101.2 joules. Okay.
Yes, ma'am.
Yeah. Let us move ahead. You want to take some break? You can take Manav 2 minutes.
Okay, ma'am.
Application of the gas we will take it then. Okay, this is the application. Let us. Yes, you are back.
Yes, ma'am.
So here, this is actually a revision of that. In this case, the way we were doing that, isn't it? Combined gas equation. That is PV is equal to nRT. Supposing you take two different conditions wherein pressure changes, volume changes, temperature also changes. Then we can write this equation as P1 V1 is equal to, while the number of moles remains the constant, okay, N or T1. Similarly, P2 V2 is equal to N or T2. Okay. Divide one by the other. This is equation 1, this is equation 2. When you divide this NR gets cancelled, isn't it? You will get this equation. Correct? So you will actually get P1 V1 divided by P2 V2 is equal to T1 divided by T2. You need to arrange it. So you will get P1 V1 divided by T1 is equal to P2 V2 divided by T2. So sometimes we use this equation as well. This is also a combined gas equation, okay? In fact, very important equation among all these laws. Now in this case, Avogadro's law that we did, isn't it? So there also we can write an equation. We said V is proportional to N. The moment when you write this, V1 is proportional to N1, V2 is proportional to N2, divided one by the other. Then you will get V1 by V2 is equal to N1 by N2. So this kind of equation we can get for get wherever we want. Only thing is we should know this equation. That's it. Okay?
Yes, ma'am. We had to prove that equation in units and dimensions to see if
Yes,
to find
that
the
is
unit.
true. Yeah. That is
To find
actually
the powers.
Yeah, true. So that is actually you have to do when you take up the problems. Units are only important there. Determine the volume occupied by 4 gram of oxygen at STP. So it is simple one because we know the volume, isn't it, at STP, that is 22.4 liters, occupies a volume of is occupied by 32 gram of oxygen, correct? 32 is the molar mass of oxygen.
Yes, ma'am.
Therefore, 4 gram would occupy.
.8 now.
Yes.
2.8.
2.8, okay? Yeah, that should be the answer for this. 2.8, okay? Yes. Fine. Let us see for this. 4-liter sample of a gas at 30 degrees centigrade, 1 atmospheric pressure is changed to 0 degrees centigrade, 800 torr. What is the final volume? So you have 4-liter sample, 4.0 liter sample at 30 degrees centigrade, 1 atmospheric pressure is changed to 0 degrees centigrade and 800 torr. You have to convert either this into atmosphere or that into torr. Okay. So what is the final volume? This volume we will have to conduct. So you have to use P1, V1 upon T1 is equal to P2, V2 upon T2. Temperature needs to be converted and even the pressure. 760 mm is equal to, or torr is equal to 1 atmospheric pressure. So therefore 800 is equal to, you can do it this way. So 1.05 atmosphere. That you can use. This is 1.8 atmosphere. So P1 is 1 atmosphere into V1 is 4 liters divided by T1 is 273 plus 30. This will be equal to P2 is 1.05 atmosphere, 0.5 it is, atmosphere into V2 we need to find out, divided by 273 plus 0, that is 273. So when you calculate this, how much you will get, just see. Is this a value which you're getting?
Just 1 second.
Yeah, no problem.
Yes, ma'am.
Oh, move ahead. This one is the system and all these things, you just ignore this because we will be doing this in detail in thermodynamics. Okay, let us concentrate on this gas, which is our system. Okay? So in this case, initial is PV, T and N, and final is pressure. Pressure volume has remained constant because this is an open vessel and the gas can be up till here. Rest of the things it escapes. So number of moles changes, temperature changes. So therefore we will get this equation. So PV has remained constant. So N1 T1 is equal to N2 T2. This equation also sometimes we use. Okay. So that is up to our experiment problem. Okay. Any two can be kept constant. PV is equal to NR. R is as it is a constant. These two can be kept constant. Volume temperature can be kept constant, whichever way. Okay. Like depending upon that, we will derive that equation. Applications of gas laws, LPG cylinder, till the time temperature remains constant here, pressure also remains constant. Okay, but then no gas has been, it is, and when it is not used, okay, the number of moles remains constant. Under these conditions, if temperature remains constant, pressure also would be constant. But what happens is, as we use this, number of moles decreases, then pressure automatically decreases. That is what about this cylinder. As you use the cylinder, the moles of gas gets used up and pressure decreases. Next one is this one. This is an important application because we use it actually during summer. It is actually done. So what happens is, the tire car which is inflated to its maximum volume is this. During summer, temperature increases. So because temperature increases, pressure also increases. So if we don't, adjust the amount of the gas here, then there is every chance that it is going to burst. Okay, so and at that temperature during summer, especially, the pressure inside this tube is kept little low. That is the suggestion that is given by all the people who check the air pressure there, right? So that is the application, second application. So in this case, volume remains constant, number of moles, R is a constant, this is a constant. If you put that, P is directly proportional to N. Pressure is directly proportional to N. So in that case, if pressure is more, we need to decrease the number of moles. You need to remove some air from here. Then only pressure could be maintained. Okay.